Hello, everyone. Thanks for coming to the webinar. Today, I'm here with Mark Fisher. My name is Mark Pollack, and we're going to be presenting the latest iteration of software that we've created for doing data microservices in the cloud called Spring Cloud Dataflow. Both Mark and I are co-leads of the project. So the use cases that we're trying to address with this project are fundamentally how do you move data around, for example, ingesting data from a variety of sources such as HTTP endpoints or traditional messaging middleware sources such as JMS, or newer ones that are quite relevant in today's enterprise such as Kafka, and of course the good old file that really will always be around. And you want to take this data from these sources and store them in a variety of sinks. So HDFS for using Hadoop's ecosystem of tools to perform analysis on, maybe Cassandra, maybe Hawk, which is Pivotal's SQL product on top of HDFS. And of course, there's a good old JDBC. File to JDBC is a common, typical enterprise data movement. So the use cases really are about moving data from left to right in this diagram. And in particular, this could be a lot of data. You're going at high speeds across your network, ingesting, and you want to gain some insight in that data in real time. This could be looking for particular fields in the data, potentially evaluating a data model. And so this is the kind of space that we're trying to address with Spring Cloud Dataflow, and also is what we were trying to address with the previous generation of the Spring Cloud Dataflow project called Spring XD, which some of you might be familiar with. Here I'm just going to quickly go over the architecture and the basic DSL we had for expressing streams in Spring XD. So in the upper left-hand corner, this is representative of the DSL, external DSL that you would type into, for example, a command line shell. And we use a UNIX pipes and filters format where you define a stream as being an HTTP source and then pipe to a Cassandra sink. And similarly for, let's say, the source being JMS and piping it to a GPF disk sink, which is how you get data into Greenplum database or Hawk. And we made our own runtime that was sitting inside the XD admin. It coordinated the launching of these sources and sinks through Zookeeper. And if you launched a stream called HTTP pipe Cassandra, essentially a little application HTTP would rise up in one of these containers, and for example, the Cassandra sink would go into another container. So you could sort of make an analogy that these containers were equivalent to a servlet container, and all of them were really sort of like WAR files that you would deploy in. So you could have multiple of these sources, for example, living in the same container. And what's important here is that they communicated through a message broker, Rabbit or Kafka. And where we deployed this was really, you could use VMs. Of course, you can use VMs for anything, or just deploy it on Metal. And we provide this runtime to make sure that if something happened to that container, we would redeploy it on another container to make sure you had high availability. And as we got into the project and we got a lot of feedback from various customers and users, various sort of questions came up about how should we scale up and down the instances at runtime, how do we change versions, basically, of the module. We call them modules, these JMS sources or Cassandra sinks. And another issue that came up really is potentially you might have an application or one of these modules that needed more memory than the others. So maybe it needed more disk as well. And so we needed a way to specify, on a per application basis, what you would use for memory and disk. And although it's not very obvious from looking at the diagram, in practice, the way we structured things with this container meant that we had a pretty large amount of classes in the parent class loader. And if you created a module, it was very common that if you'd use a different version of one of the jars we had in the parent, it would lead to sort of hard to debug class loading issues. And that was really symptomatic of having so many libraries in the root class path. So we took this feedback and decided that we really needed to make a major shift in our architecture. And I think now the architecture we have is really great and is really in sync with really the modern sort of ecosystem of platforms that run applications, platforms as a service, and other platform runtimes. So the big shift that we had is we went from these multiple modules embedded inside a container to really just having individual standalone executable applications. So literally applications that if you wanted to, you could run by typing Java minus jar. And the even bigger shift for us was realizing that there was quite a maturity in the platform space, and we're going to end up duplicating a lot of functionality that exists in other platforms. So we left our Zookeeper-based runtime behind, and now we delegate to existing platforms. And I'll talk about those a little bit later, which ones that we support. So the term data microservices is not a very common term. I think actually we're probably going to stop using it as a terminology to describe what we're doing. Essentially, they're standalone applications that are focused on data processing. They communicate with each other using, quote, lightweight mechanisms. This really comes from Martin Fowler's blog post on the introduction of microservices. It's very common for microservices to communicate over HTTP, but there's also mention there of using lightweight messaging middleware, specifically mentioning things like 0MQ or Rabbit. And essentially, because we're using messaging middleware, it's an event-driven paradigm, so I think perhaps a better term for this are event-driven microservices. And they typically are dealing with data movement. So one thing that I think is another good 10,000-foot introduction to kind of wrap your heads around the sort of architectural theme of what we're doing is to look back at the sort of principles behind UNIX. And they're sort of summarized in these 3 statements that I cribbed off of Wikipedia. So you should write programs that do one thing and do it well. You should write programs that work well together, and write programs to handle text streams because it's a universal interface. And so if we did a really robust, I guess, version of word count in a Unix shell, you can see we cat the contents of a book, and then we start passing through the pipe symbol to various other commands the appropriate information to normalize it and look for the words and then sort them and print them out. So our DSL now is really very much aligned with this Unix philosophy. Each part in this DSL expression that we have in XD really represents an individual application, and they're not communicating over text streams as they would in the Unix shell, but they're communicating over messaging middleware. So I think the analogy is really quite a good one. So what type of applications do we have in Spring Cloud Dataflow that we are interested in? There's really 2 generic types. Apps that are long-lived, which stand up and run, and they need to exist for a long time. So for example, the HTTP source going to an HTTPS sink, you want this to happen 24/7. And then short-lived task applications. These are typically batch applications that you might schedule to run and could last anywhere from a couple minutes to many hours. And in the course of going from Spring XD to Spring Cloud Dataflow, we split up the project into multiple sub-projects. And so now you can create these long-lived stream applications using APIs that are available from a dedicated project we have called Spring Cloud Stream. And similarly, there's an abstraction for running batch jobs that we call Spring Cloud Task. So Spring Cloud Stream and Spring Cloud Task, these are the basis of what you would write if you were writing custom applications. And the APIs for Spring Cloud Stream and Spring Cloud Task we're going to show in the next couple slides. So what I'm going to do now is I'm going to hand it over to Mark Fisher, and he's going to walk through a lot of the details of how you use Spring Cloud Stream and how you start to then build up this collection of applications to put into Spring Cloud Dataflow to deploy on a bunch of platforms. So I'm going to pass it over now to Mark.
Okay, thank you. So Spring Cloud Stream, as Mark just mentioned, is the project that we basically extracted out of the Spring XD ecosystem in order to have a programming model and a runtime that was based on Spring Boot, so you could build autonomous executable applications outside of the XD runtime. So what used to be a module in XD is now simply a boot app, and Spring Cloud Stream is the project that you build on to build those boot apps. Because it's built on Spring Boot, that means the infrastructure is provided via auto configuration. So all of the third-party dependencies, all of the whichever messaging middleware you're using, and the configuration and setup of that messaging middleware is convention-based and driven by those auto configurations that are included as long as you have the boot starter on your class path for building a Spring Cloud Stream application. So as a developer, that means you add the starter to your Maven POM or your Gradle build config, and you're basically up and running right away. And the model in Spring Cloud Stream basically consists, or the most important part of it is this binder abstraction. And the binder abstraction allows us to have pluggable messaging middleware options. So you can use Kafka, you can use Rabbit, there's a few others that we've started working on. And at the level of the abstraction that we defined, there are some opinionated primitives. For instance, the actual message exchange occurs through a persistent pub/sub topic. And on the consuming side, we have consumer groups. So you can have multiple applications belonging to a single consumer group, and then messages will be load balanced across those applications. If you need to rely on partitioning based on a key in the message data, then the load balancing across instances in those groups can be driven by that partitioning scheme. So this actually maps very closely to some of the messaging platforms out there today, such as Kafka or Kinesis or Google PubSub, matches very closely to those models, and not as closely to some of the others like RabbitMQ. But through this abstraction, we're able to implement and adapt the underlying messaging middleware to fit this model. But it will be very familiar to anyone working specifically with something like Kafka. And that's what it's really based on. What this means for the developer then is your application actually is focused on just the programming model of dealing with the incoming data objects and the output that you're generating. It might be that you're building a source application, in which case you're only generating output, or you might be building a sync application, so you're only processing input, but you can also implement a processor which actually takes input and produces output. In all three cases, regardless of the type of app you're building, you don't need to worry about the underlying infrastructure. You don't have to worry about the actual messaging API, like the Kafka API or the Rabbit API. You just write your handler method that can accept and process the data items. And that itself is, because of the way we've written our binder abstraction, it can actually handle adapting to different kinds of handler methods. So that can range from anything like Spring integration style, one message at a time being processed, where you either accept the POJO, which is the payload of the message, or the full message itself with a payload and its headers. Or you can even adapt to other programming models. For instance, you'll see in an example slide soon that we can support the Reactor API as well. So at that point, instead of dealing with a message at a time in the programming model, you're dealing with a Reactor type called a flux, which is a representation of a stream and gives you streaming operations. So there's flexibility there in terms of what type of application you're building, what kind of throughput you're expecting, what kind of analytics you may be doing as a developer. Okay, and then on the next slide here, you see an example of, again, as Mark mentioned, these apps that you build with Spring Cloud Stream are self-standing autonomous apps that you can execute using Java-jar. Here you see an example of basically building a pipeline that would be Twitter to Cassandra, but doing that by running them as individual applications, Java-jar. In both cases, there are several boot configuration properties that you can provide, and this will include the boot configuration properties that are specific to that particular application. So in the Twitter example, you see the consumer key and the consumer secret. In the Cassandra example, you see the query that's going to be executed. And then there's also boot configuration properties for the Spring Cloud Stream project itself. And here you see the most important one, which is the destination for the binding. So on the source app, there's an output destination, and on the sync app, there's an input destination. And by sharing the same topic name there, those will then be connected over the messaging middleware based on which binder is on the class path. So you would be running both of these applications with, say, Kafka binders on the class path for each, and they will then be communicating over a Kafka topic called data dest. And the Cassandra app will join a consumer group, will be part of a consumer group that subscribes to that topic, and the Twitter stream source will be sending its tweet objects to that topic. And so that's how they communicate with each other directly if you're working at that level. If we go up a level, we rely on Spring Cloud Dataflow to do the orchestration for you. And so in this case, what you get is the benefit of DSL, and you don't have to worry about passing those properties for the Spring Cloud Stream destinations. That's handled by Dataflow itself. The other configuration, you don't see them in this particular example, but the other options like the consumer key and consumer secret can be passed into the DSL using -- syntax here as if it's part of really similar to a UNIX pipes and filters model. So at the top we see a stream definition, and the stream definition consists of tokens separated by the pipe delimiter. Those tokens would then be the name of an app that's been registered with Dataflow. So that means there's an underlying app registry. I would register Twitter Stream as the name and then point to the URI for the actual resource that represents the Twitter Stream jar file. And that could be a Maven artifact, so providing you Maven coordinates, or it could be a Docker artifact. It depends on the type of application platform that you run Dataflow on. If it's a Docker-based platform like Kubernetes or Mesos, then you would specify, you would use the Docker artifact paths in your app registry. And if you're relying on Maven, say running it standalone or in Cloud Foundry and you have reference to a Maven repository, then you would use Maven URI coordinates when you register these apps. And then once they've been registered, you just refer to them by the name you register, the key that you registered them with in the DSL. And under the covers, it's going to execute the boot applications, and it's going to provide the configuration properties that they need. So we mentioned that the model is based on a pub/sub semantics with persistent messaging. So this is where the various binder implementations provide this functionality for you. If you're using Kafka, then it would be the HTTP source in this example would be sending to a Kafka topic, which is named after the stream name and the module that's emitting those messages. If you're using Rabbit, then instead of it would be sending to a topic exchange. And on the consuming side, if you're using Kafka, it would be literally using a Kafka consumer group. If you're using Rabbit, it would be creating a queue for each consumer group and then the consumers binding to those queues. So the abstraction is the same from the developer's perspective. And as I mentioned, we're also starting work on several other binder implementations. So the JMS implementation and the Google Pub Sub are in progress, and we've started looking at Kinesis as well for when you're running on Amazon Web Services. Okay, and then another feature here is to be able to use named destinations instead of an application in your stream definition. So here you'll notice that we're using the greater than sign instead of a pipe. And what comes on the other side of the greater than sign is then literally the name of a destination within your messaging middleware. So this, whereas all the other streams that we've seen so far are linear pipelines, this allows us to start to build graph structures for our data flows. In this case, all three of these source apps, HTTP, JMS, and S3, are emitting their messages to a single topic. And downstream from that topic, you may have just a single sink that's then basically joining the data from all these sources. Or you could likewise be using this name destination on the left-hand side of the stream definition, followed by a greater than sign, and create a fork in the data flow path as well. Okay, and then we have this concept of consumer groups. What this shows is an example. Once you are sharing a topic across more than one consumer group, what happens here is each message that is sent to that topic will be sent to each group. And within a group, those messages will be load balanced. So in this case, in the HDFS group, we're basically going to be receiving every other message across these two instances. And the counter group, since there's only one instance, that app instance will receive every message. If you scaled out the counter group, then you would be load balancing there as well. Another interesting thing about this particular example is if you look at the syntax in the DSL, on the S2 stream, it's actually starting with the name destination, but this name destination happens to be the name of the destination that the Dataflow would generate for the other streams app. So S1 is the stream name, and then dot and the name of the module that's emitting, the app that's emitting messages to that topic. And so this is effectively how you would create a wiretap on an existing stream. And it's a pretty common pattern where you want to do something like this, where you're ingesting all of your raw data into HDFS, but you also want to do some real-time processing to count the items as they're going through, and you can do a wiretap for that. You could just as likely invert this relationship so that the wiretap is the one doing the raw ingestion. And here's another example using a tap. In this case, we're reading Twitter stream into HDFS, but we're also tapping that to do counts of the actual fields. So for instance, you can count the occurrence of hashtags and create a top-in ranking for those hashtags. And this is actually functionality that is built into the Dataflow model to the extent that our Dataflow server, in addition to handling the orchestration in the DSL, also exposes through the REST API access to the data for these various counters that we provide out of the box. So you can have field value counters, simple counters, as well as aggregate counters that will group by different time units. And we have a UI representation of that through the Dataflow server, so you can get a simple analytics dashboard up and running as soon as you create one of these streams, and just refer to that by name from the REST API or through the UI. Okay, and then I think we have a couple examples here of the programming model. So this is probably as simple as it gets, using app enable binding, which is part of the Spring Cloud Stream API. And this again follows the boot paradigm where an enable annotation brings in auto configuration classes. So in this case, it's going to be treating it as a processor. You could likewise have source or sink here as the specified interface, and that's going to tell it what kind of channels you want to create. You can also create your own interfaces that define arbitrary numbers of channels, and then those channels will be created within your app. In the case of a processor, it's going to generate an input channel and an output channel, and then you can see those are being referred to in the handler method below. The stream listener annotation is really a simplification provided by Spring Cloud Stream for what Spring Integration provides as service activator. It basically says this method is going to be handling the data that arrives on a channel, and in this case, the channel named input. Here, really, it's through this abstraction where it's not necessarily a channel, but just a destination. It could be a message channel, or it could be a reactive type like a flux. That is a further level of abstraction above Spring integration. And then the output generated by this method will be sent to the destination named output. So that's handling messages one at a time. A string is passed in each time a message is received on the topic, and then a string is emitted to the output channel. Another alternative is then to actually use the reactive API. And with the reactive API here, with Project Reactor on the class path and the Spring Cloud Stream reactive dependency, then you can use flux types for your input and output parameters instead of just the string. And what that means is here we can accomplish the same thing as the previous example, but we're using the mapping method and then providing a lambda to do the uppercase transformation of each stream. So we're actually able to consider these input and output types as the streams of data instead of individual items. And then finally, if we take this further, you can see the real benefit of using this API, which is that you get these higher level operations for doing stream processing. So here we have a windowing example where we have a sliding window that's 5 seconds in duration, and it slides every 1 second. And then we're able to do grouping within that window, and then basically taking the canonical word count example here and showing how you would accomplish that with this API. So I think the most important thing about this for the developer's experience is that you have a starter on your class path in your Maven POM or your Gradle config. You add this one annotation which actually brings in the auto configuration. You annotate the method, and then everything else you're doing is free of any concerns of the underlying infrastructure and using that API directly. It might be as simple as Java strings, or you might be using Reactor, but all you really need to know about in the implementation of that method is Reactor. There's nothing there that's requiring your attention for the fact that this is a Spring Cloud Stream app. That all stays out of the way. And I think with that, we are back to the runtime platform deployment options that we have, and I'll hand it back to Mark Pollack.
Cool, thanks. So what we saw with Mark's description is really a little deep dive into the actual programming model of the apps that we're going to deploy. And as I mentioned earlier in the webinar, we no longer write our own runtime, but instead delegate to other platform runtimes. And sort of year 2014, 15, there started to be quite a large number of other contenders, I guess, in the platform runtime space. And I guess that was sort of an eye-opener that why should we be spending time developing runtimes when clearly there's an entire ecosystem out there who are doing this full time. So we decided to sort of piggyback on their hard work in a way. So runtimes such as Pivotal's Cloud Foundry, Kubernetes, Mesos, and Yarn have been around for a long time actually, as well as Cloud Foundry. New ones like from HashiCorp Nomad and Docker Swarm. So these are sort of examples of the ecosystem, and I'm sure we could paste even more of these logos and make a NASCAR type sweatshirt for folks if we really wanted to count every single one that's out there. There's OpenShift as well. We'll talk about that in a little while. So now what we do is we still have a Dataflow server, and it's the entry point for executing commands to create these streams. We also have a designer, which we call Flow. This is a sort of typical drag and drop like experience with a palette that you can select components from and wire them up. Or of course, since it's just a REST API, you can access that directly through documented REST endpoints. So the server receives these requests and it translates them into ways to deploy the applications and set their properties, translating that from the DSL. So there's an abstract API, a service provider interface called the deployer SPI. And we have several implementations of that, and this is what gives us the portability across the different platforms. So we have one for Cloud Foundry, one for Mesos and Marathon, one for Kubernetes, there's one for Yarn. Also, there's a nice contribution from the community for OpenShift. And we also have a local one. Oops, sorry. Looks like I cut and pasted there too many times. There's also a local deployer, SPI, which is useful for running this on your laptop, just to get a feel for it when you're getting started. Let me just pass through that. So here's an example now of how this would look. So you can see two stream definitions. So for example, first one is HTTP Transformer Cassandra, and you can match those to boot apps that are on the bottom here in the diagram, and they're communicating over HTTP. Over the message broker. The database shown here is really where we're storing these stream definitions and also task definitions. And the runtime could be, again, any one of the ones we mentioned earlier. The interesting point here that I'll condense on the next slide is that one downside of looking at this through a pipes and filters type model is that it can start to get very chatty very quickly. For example, if you look at the HTTP going to transformer, it's very likely that that transformer isn't particularly doing all that much in terms of work. Yet we have another hop on the message broker, maybe just to do some simple transformation. Whereas maybe with the Cassandra sync, we might want to scale that up to scale our writes, because probably writing to Cassandra is more of a bottleneck than consuming inbound HTTP requests. So one key feature of Spring Cloud Stream is the ability to aggregate applications. So you can create an app which is really the combination of these two existing applications through an aggregation API. And so this lets you avoid that extra hop on the network wherever you choose. You have to decide this up front, but usually once you start to know your problem space, you can make these decisions up front. And over here I put a little link when you guys get the slides, and ladies get the slides. You can take a look at that API. I'll just go down over here. It's a sort of Fluent-like API. So in this case, it's bundling everything into one app, a source, a processor, and a sink. So you can say from, the source app and start passing in different command lines and then pass it off to another application. So you can read more about how that works on the online. Back to this. And how to do it. But the key architectural point here is that you can avoid this excessive chattiness. And it's nice to have, for example, at least one sort of pipe, so you can then scale out things on the right-hand side. Future version, we'll be able to deploy what we're calling application groups. So really just applications that can be completely self-contained. This might be, HTTP-based microservice, or it could be a Spring Cloud Stream app that has all of the components, a source, a processor, and a sink in it as well. So one feature we have is really around how you can control the deployment of these streams. So the stream definition that we have so far is really very logical, HTTP, pipe, HDFS. But what we might like to do is to have two instances of our HTTP endpoint in order to handle a certain amount of load. Obviously put a load balancer in front of them so they can share in the incoming request stream. Maybe we want to have 3 of our own custom processors that do a certain amount of work, and maybe we want to have 4 different instances of the HDFS sink to scale the writes to HDFS. And so we can specify that using a deployment manifest. I'll show you the syntax in a moment. And furthermore, messaging middleware, in particular Kafka, Google PubSub, Kinesis, and even we can do this on Rabbit, allow you to partition the incoming stream so that different messages that have a property that's important to you will get routed to the same instance. So for example, here I have blue, purple, and red boxes. So each of these represent a different type of event, maybe a different type of customer, for example. That is their role or their level, for example. And through partitioning, we can say, well, I would like to make sure that only the blue points, the blue customers, let's say, go to this node, only the purple ones go here, and only the red ones go here. And the reason this is important is, you might want to create certain calculations that require you to always get the entire incoming stream for that particular customer. Or another good example is sensor data. Suppose you wanted to compute the windowing average of a temperature sensor. You need to have all of those the same sensor, send the data to the same node in order for it to perform the calculation correctly. And so the way we do this is what we call a deployment manifest. You can specify these in a property file, or you can specify them on the command line when you're using the shell. And so these two aspects of a stream lifecycle, creating and deploying, they're two separate steps. The create part is really sort of the logical flow, and the deploy step is sort of the knobs you get in terms of how you can change the instance count, for example, which is simply done by specifying app dot, now the name of the app, which corresponds to the name used in the DSL expression, and then count. And for example, in this case, we wanted to have partitioning done on the consumer side of the work processor. And so the property HTTP producer specifies that producing end, and it's going to partition the data based off of the ID that's in the payload. So meaning we expect there to be a field called ID, either in a Java object or in JSON object as well, to do that sort of property path style navigation. And then it will set up the appropriate middleware to perform that work. Another one is around resource management. This is a pretty simple one. You can go deploy, let's say, to Cloud Foundry, in which case you can choose the memory and the disk size. So if, for example, you had more resources that were required to do your custom processing, when we deploy it, we'll ask the platform for, in this case, 2 gig of memory instead of the default value, which is lower. So it'll be able to handle the load that you're putting on it correctly. So that's really quite a lot on streams. It's quite a popular thing, of course, right now to talk about stream processing. But one thing that will never go away is, of course, batch processing. And we have this project called Spring Cloud Tasks, similar in a mirror image, really, to what we're doing on the Spring Cloud stream side. It's a boot-based framework that has auto-configuration, and its responsibilities are to manage short-lived processes. So essentially, it keeps track of every task you start, and when it starts, and the status of it when it ends. So you could do reporting, for example. Did this task succeed or fail? The task could launch any short-lived code, doesn't matter what. But of course, since we have our own batch platform under the Spring Batch umbrella, we provide a lot of support to integrate with Spring Batch. So the way we deploy to the platform is similar, really, as in the case of streams. We're just launching one app. In this case, it's a short-lived app. So you can create a task and pass in certain parameters that characterize that individual task, and then launch an instance of the task. And this is just posted in the same way over the HTTP endpoint using the REST API of Spring Cloud Dataflow server. That's persisted in the database, namely the start time, end time, exit code, and so on. We'll launch, in this case, I'm showing the JDBC to HDFS app. And what's interesting is that we also have communication with the message broker so that, for example, you can know when the task is started and stopped. So this allows you to create a stream definition that will consume, for example, from the task event destination. If it's a Spring Batch job, like in this case JDBC to HDFS, a Spring Batch job, let's say, you also get an event stream for all of the lifecycle hooks that are available in a Spring Batch job. So when the job starts, using the terminology of Spring Batch, when the step starts and stops, item read events, process events, write events, and skip events, which are really, in a sense, events that are errors. So this lets you, for example, create an error stream so that you can watch for errors in your batch job. So this kind of two-way bridging between streams and tasks is quite important when you're making a complex use case. Similarly, there's a sync that you can have in a stream which will launch one of these tasks programmatically. So this works, on all the platforms, and we have sample apps that show you how you could integrate with Spark, basically launch a Spark app, Scoop, and also traditional Spring Batch. And this is an example up here of a stream definition where you can use the HTTP source as a sort of ad hoc means to trigger one of these tasks, so essentially allowing you to do it somewhat programmatically or through some use of some scripts, launch a task at your convenience with a simple HTTP endpoint. So here's a programming model. This is a canonical Hello World example. Again, it's a boot application. The appropriate infrastructure that is used to create the tables in a database to keep track of when the task is started and when it has ended and the parameters passed to it is all done through the enable task annotation. So as long as you have on your class path one of the starter projects that will bring in the appropriate platform dependencies, depending on where you want to run it, you'll be able to use standard sort of Spring Boot command line runner functionality to launch this particular short-lived task that just prints the time. So we focus quite a lot on writing your own app, showing you the programming model, but we produce artifacts for quite a large number of common use cases, mainly a lot of sources and a lot of syncs. So you can consume data from Amazon, Cassandra, HDFS, JMS, and whatnot. So we have now probably around 60, 70 of them. They're currently housed in this two GitHub repos. So you can check that out, browse it, and see what's available, and hopefully what you want to do in terms of your use case is already there. So it's much less for you to write. You can just get started very quickly. If you want to customize or compose them, aggregate them, like I showed earlier with the HTTP and Transformer example, you can go to this website, Start SCS, Spring Cloud Stream, CF Apps, and that will bring you to a web page which is very much like the start.spring.io page and allows you to customize and create an aggregate app. If you just want to create a complete, out-of-the-box, fresh let's say processor or task, you go to the standard start.spring.io page and you type in stream or task and you'll see the appropriate drop-downs. I'll show that in a little while. And once you create these apps, when you start Dataflow as a server, it really knows nothing about them. You have to register them. But what we do is we provide a long list of all these apps if you want to just get started quickly with the local version, for example. And if you follow this bit.ly link, this will basically import all 60 for you at once, just as a convenience. But usually the normal case is you're going to pick the 5 or 6 that are relevant for you and register just those with Dataflow. So it's aware of the mapping of the DSL name to the artifact name. Just a quick look at the new designer we have. It's pretty slick, I think, very, very nice in terms of the style and the design. And what's being shown here in particular is sort of quite useful. It's an example of a scriptable transformer. So you can put code in there, either Python or Ruby code or JavaScript, and then have it executed on the fly when you deploy this stream. So it's kind of good for very quick and dirty manipulation where you don't want to quite create your own application, but just need a little bit of custom logic, and you could use any of those, or Groovy as well, as a script. So for those coming from XD, I just do a quick rundown because I get this question quite a lot. The components in XD here on the left-hand side, those for Dataflow are on the right-hand side. What was the admin server? Now we just call the local, the Dataflow server with a bunch of different implementations. So local It's good for development, Cloud Foundry. You can run on Yarn, Kubernetes, and Mesos. We removed the whole concept of the container, so it doesn't exist. What we called modules, now we call applications because they are standalone. You could just execute them with Java -jar. The admin UI is basically the same in a way, but we emphasize it more as a dashboard now. And message bus, we talk about the message broker a lot, but the different types of middleware you use, we refer to as a message bus in XD. And now with the Spring Cloud Stream model, they're really the binder implementation that's used to bind to the particular middleware. And we've sort of opened up the name of a job to be the more generic task terminology. So with that said, I'm going to do a quick demo showing you how to use this on Cloud Foundry and also on Kubernetes. Let me just pop out of this and pop into the Linux VM I have. So start that spring.io, you can go here and you can type, for example, stream. And you'll see there's a stream rabbit, for example. You can select this, my demo app. And this is how you can create a application just right out of this download, unzip it, and basically you'll get a very simple structure like shown here. This is in this case, I typed uppercase transformer as the name of the app. And all we're doing here is really mimicking what you saw in the slides. I have the enable binding annotation as a processor. So that means it has an input and an output. To avoid just typing bare strings, you can use these static values. And I'm just going to create a simple processor. All it does is uppercase. So really hardly any code here, and really all of the demo is about showing this on a different platform. So I've already made a jar file, I've posted it somewhere, and similar for the case of Kubernetes with the Docker Docker artifact image. I don't want to really spend a lot of time waiting for uploads. Similarly, I've already uploaded the Dataflow server itself to Cloud Foundry. And I've using the internal database, actually. I didn't bind a MySQL database to it, but you could. And this is sort of up and running here already. There's the log file of it. Probably some requests from my previous demos. And the way you interact with this, let me just exit this, is through the shell. So that's Spring Cloud Dataflow shell. Just start that up. And now when it starts up, you really have to point it to the appropriate location. And so if you go to, let's say, overview here, or routes, right, that's where this is living. So I can copy this link. And I can say Dataflow config server. I want to configure where the server is. It's living over there. And now I'm connected to that server. And there are a bunch of commands in the shell. Let me just scroll and show you a few of them. So there's stuff related to apps. I can import apps. I can register them, unregister them. I can create streams. Here we go. Create streams. I can deploy them. I can destroy them. I can list them. And similar for tasks. So if I do app list, these are the three apps that I registered previously, HTTP and log and transformer. If I want to get some information, actually I'm hitting tab here. There's a lot of tab completion. So if you're ever stuck at the command line, don't know what to do next, you can type app info like --ID, and I say sync log. And this gives you the different options you have to set on the log. So its name, its level, or in this case, there's one for an expression, so you can evaluate that against the incoming message. And the default value and the data type. So what's really important here is I'm just going to create a stream. I'm going to call it HTTP to log. Here's the definition. I'm going to use HTTP as the source. My transformer, I just hit tab and it typed it out. If I hit tab now, ooh, I don't want to do that. Let me, you see I could pipe it into log, or I can chain another transformer and give it an alias. But I'm just going to let it go to log right now. And I'll deploy it in one step with the option deploy. So now this is communicating to the Dataflow server that's sitting on Cloud Foundry over here. And I can go to the user interface of that. Here are the applications that are registered. Here's the stream definition. It's not really failed. It's starting up. And if I go to here first, that's probably easier to see. These guys are starting up. So this is HTTP to log. That's the stream name. Can't make it bigger, unfortunately. And this is HTTP to log the stream name dash log. So that's where we're going to see the output. And then this is the transformer. So if I click in here and look at the logs, we'll see that it's starting up, creating the container, starting the health monitoring of the container. And here's the mangled boot logo. See if I can make that a little bit bigger for folks. So there's a Tomcat started on port 8080. So now if I go back, let's say to this runtime, yep, now you see they're all deployed right here. I'll make this a little bigger. I help. So log is the sink, HTTP is source, this is the processor. So if I get the endpoint, for example, for the HTTP source, let's see, which is this one. Oh, actually it was right over there. There's the route. Let me just cut and paste that. So I can go back here. And what I can do is to HTTP post. Oh, first let me do this. Here's the apps using the CF command line. And I can just look at the logs, for example, in this case, of this guy. That's the end point. So it's telling the logs. So there's a little helpful debugging command called HTTP post. And I can just now paste in target. Oops. Typo. And I'm going to send it hello webinar. Oops. Oh, I should be posting to the HTTP endpoint, not the log one. There we go. So now, hopefully out here on the top, we should see hello webinar in uppercase. And now since we're on the Cloud Foundry platform, we can do something like scaling it. So I can now take the log sync and do CF scale this app. So it's going to scale this up. If I go back here, it's in the act of deploying the second one. So if we just have to wait a little bit. Oh. So it's in the process of starting up the second one. There's the log file. So it's getting close. The booting up. if it's good. Yep, it's deployed now. So if I go back to my, I could have just looked over here as well. So if I go back now to my hello webinar, I'll just make this hello webinar too. And I start posting a lot to it, same message over and over. What you'll see here is that it's load balancing this notation app/1, app/0. It's load balancing across the 0th instance and then the first instance of the app. And similarly, what I can do is go to Kubernetes. So I've also deployed here in Kubernetes using the Google Cloud Platform. So I have my own cluster here, scdf-Pollack. And I should mention in the previous case with Cloud Foundry, I was using Rabbit as the binder. Here what I've done is I've set up Kafka as well as a MySQL database. And this is the Spring Cloud Dataflow server. That's the replication controller, and the pod instance is down here. There you go, down there. So same thing, I run the same shell. Oops. So if I want to know where things are running, for example, kubectl, I know that my MySQL, that the Spring Cloud Dataflow server is sitting on this port here. I'll just cut and paste that. So I'll do Dataflow config, oops. Paste that in. The port is 9393. So I can do app list, and these are the ones that I've registered here: HTTP and log, and the JDBC sync, and the timestamp sync task. Sorry. So I'll just create a simple one here just to show you. I won't go through the same exact one with the transformer. Definition type log. And I'm not going to deploy it with the -- deploy because there's one more property that needs to be set. You need to indicate to create the load balancer explicitly in the case of Kubernetes. I'm just going to go back to my history here in the shell. So I'm going to deploy the stream test, but pass in this cloud deployer Kubernetes create load balancer equals to true property. That means I'll be able to access the HTTP endpoint externally. So it's going to create an external. So if I do the get service again, see it's starting to launch the HTTP pods that are sitting behind it. And what I just have to do is wait for this to assign it an instance. So meantime, if you look at the dashboard, just refresh that. You'll see here is another replication controller and the corresponding pod instance. If I go to, let me actually reload this, the logs that you have available. So I'm in that, and I'm going to look for this log. Stretch that out a little bit. And then tail it. There we go. So there's a bunch of noise here related to the health checks. Whenever a health check is performed, it prints out this information about Zookeeper and whatnot. But what we'll do is, here's the UI running on Kubernetes, and so the HTTP log is deployed. Oops, sorry. So if I go back to this, see the logs there. Go to the shell again. Maybe here it is. So I'll just do the let's get the IP address. Yeah, so there it is. That's the external IP address. So now I'll do HTTP post target. Put that IP address in. That's 8080 by default. Post a bunch of them. And then just do this toggle again, I guess. Hopefully. Yep, there it is. So you can see the data just flowing through. It's not uppercase because we don't have the transformer in the middle, but you can see the data flowing through in the log here. I'll try to make it bigger. It's a little hard, but down there on the bottom. And that's the last of the demos. Let me just go back to the presentation. So basically, you saw a similar type of very simple stream, our Hello World stream, that showcases how you can push basically the same type of stuff to different platforms. And of course, in the real world, you're going to do stuff and storing in different data sinks, most likely, not just a log file. So some of the things that we're going to have in upcoming features, one is integration with LDAP. Another one is a nice designer for jobs. So visually, you can create composite jobs, basically stringing them together to create much more complex workflow. And then other things looking forward, role-based access. We have still to tackle the case of how we want to handle version upgrades. So going back to the beginning of the presentation where we had a lot of the shortcomings, I think we've addressed almost all of them, mostly by deferring that complexity to the platform. But the version upgrades is something that we're going to tackle. Each platform has their own sort of ways of doing that. We also hope to involve another open source project called Spinnaker for some interesting canary-style deployments. We want to deploy apps that aren't just Java apps, but for example, they might be Python apps. This way we can have more advanced analytic scenarios. Always keep increasing the number of provided sources and sinks and tasks so that there's less for you to do and just you can get started right away. Monitoring and metrics is a very important thing. We have some basic monitoring and metrics right now, but we like to get much more visibility into the details of what's going on. And what's nice being part of the Spring Cloud ecosystem of projects is we can start to benefit from other projects in Spring Cloud, in particular the one called Spring Cloud Sleuth, which is around distributed tracing. So we hope to be able to use this to show how the message flow is going across the entire set of applications in your stream. So those are sort of sneak peeks. There's a GitHub issue tracker that's public. All of that information, including all of the sub-projects that we mentioned, you could find by going to the Spring Cloud Dataflow page. And you're going to be creating custom apps, then the stream and task projects of Spring Cloud are relevant. And if you're curious as to how we take the deployment request and map it onto different runtimes, the core SPI for that is in the Spring Cloud deployer project. And there are links to different implementations there. So with that, that's the conclusion, really, of the presentation. Let's take some questions.
Mark, first question from Philippe Gutierrez at Pivotal, and he says, hey, once you have a stream deployed in Dataflow, how do you upgrade that stream without sort of having to deal with the undeploy and redeploy, kind of like blue-green style? Is there a way to do that?
Yeah, luckily you caught us at a good time. If you look at the whiteboard right behind myself and Mark Fisher, it's exactly what we've been designing for 1.2 release. So the general idea is that you'll be able to update the properties of a particular app in your stream and also update the implementation. So we're just going to start to keep track of a lot of versions of things. We're not going to allow, at least the kind of thinking is you to change like drastically the shape of the stream. And then slowly roll out, let's say, V1 and roll in V2. So we're also planning to look to integrate with Spinnaker, which really gives you a much more sophisticated workflow on top of a basic app change, things like scheduling and automatic canary testing, where you can ask significant questions to see if the new version of your app is correct, and then if it is, ramp up the number of instances and so on, and ramp down. So basically, that's a big missing feature for us, and we're planning for it to come out in the 1.2 time frame, which I believe is, let me look that up actually while we're here very quickly. Let's see. February is currently our schedule for delivering that. So the answer is right now, you can't, unless you do it manually under the covers.
And I don't think that's something a lot of other platforms are even looking at, right? I mean, this is going to be something that's, I think, fairly unique to Spring Cloud Dataflow due to the architecture. Wouldn't you say?
Yeah, I mean, for example, I'm not sure exactly how it's done in other platforms, really. I know Google Cloud Dataflow supports a way of doing updates to the definition as well. So certainly things like Storm, for example, is a good one. It's kind of old by today's standards, but it didn't have this capability either. So I think it's something that we're doing and others are starting to do as well. And that's, in some sense, the role of Spinnaker as well, is to start handling continuous deployments. So I say that's an active area of development. Maybe there's a handful of platforms that have it now, but yep. I'm sure if you fast forward a year or two, many of them will have that capability.
Gotcha. Thank you, Mark. Next question comes from Mary. She asks, does Spring Cloud Stream interoperate with AWS Stream? And if so, how?
I'm not sure what is AWS Stream. Do you mean Kinesis? Or I don't know if a person can reply.
She can use the Q&A panel to clarify the question for sure.
Just one thing to point out, if we are talking about Kinesis here, then we have started exploring the Spring Cloud Stream binder implementation of Kinesis. The model for Kinesis is very similar to Kafka. So it's just a matter of implementing a binder that would run when you are deploying on AWS and using Kinesis. Otherwise, things would be very similar as they are with Kafka. So we've started that work.
Yeah, it turns out to be actually fairly tricky in the sense that I was talking with the developer who was working on that. The Kinesis API that Google provides is not very performant at all. It's essentially HTTP based, and they make a gRPC one, but in our testing it turned out to be even slower. And then Spotify, who was really one of the big users who switched to using, that was Google, PubSub, my mistake. Anyway, I got confused between Google PubSub and Kinesis. My apologies.
No worries. I think we don't have too many other questions. I think the last one that I hear pretty frequently is, is Spring Boot required for Spring Cloud Dataflow? Could you talk a little bit about that, and then let's see if any other questions come in, and if not, we'll wrap it up.
Sure. So there's really two aspects to this. One is when you're talking about the Dataflow server itself, it is a Spring Boot app, and all of the configuration properties are boot properties. So the Dataflow server is a boot app. The apps that it deploys today are basically Spring Cloud Stream or Spring Cloud Task apps, and all of those are also boot apps. So in that sense, it is required. But one thing that we're exploring is the ability to deploy other types of applications, not only just simple Java apps that are not Spring apps and not Spring Boot apps, but also we've even started exploring a Python implementation, which would be using the basically a version of the binder implementation, but within Python, and you would be able to deploy those apps through the deployer project. So once we have that support in place, then Dataflow, you could, in theory, have a stream where, say, a processor in the middle of between your source and sink is actually a Python application, and obviously not a Spring Boot app at that point. All we really do ultimately is pass along environment variables that from the stream definition. And so that's the way we're looking at that going forward.
Mary clarified a question and just said she's mostly curious about the interoperability among the different sort of cloud, stream, Dataflow offerings that are out there in the market. So that was more kind of her angle.
Right. So yeah, typically if you are doing streaming on AWS, you'd be using Kinesis, and a lot of the events, a lot of the sources in an AWS environment are going to be emitting data into Kinesis. So having this Kinesis binder would allow you to have a Spring Cloud Stream and interoperate with those AWS sources and sinks.
And are binders something that users can create their own versions of, or is that something?
Sure. The binder SPI is pretty straightforward, but we don't really expect users to be implementing binders. We have a JMS binder in progress, and a Google PubSub binder, and then this Kinesis one. But the idea with the Spring Cloud Stream apps is you start with the starter, and then you can add whichever binder you want in your implementation and build the jar from that. So you could build any of the Spring Cloud Stream apps today with the Kinesis binder as soon as it's available, and we'll probably be auto-generating those like we do today for Kafka and Rabbit.
Great. And for anyone that for anyone that might be looking at Spring Cloud Dataflow and thinking to themselves, "Hey, wow, this looks really, the technology looks really interesting, but it's kind of a 1.0 product that's just sort of, we just really, Pivotal just released it, and the Spring team just released it, a month ago." Maybe could you talk a little bit about what other Spring projects have sort of contributed to, the maturity of this initial release besides just Spring Boot?
Sure. Well, so Spring Cloud Stream builds on top of Spring Boot as well as Spring Integration. And for the Kafka binder, it builds heavily on the Spring Kafka project. We also have, with the 1.1 version of Spring Cloud Stream, we now integrate support for Reactor. So you can use the reactive types, such as a flux, within your message handling method. And that gives you all kinds of capabilities in terms of windowing operations and so on. We also use, and a lot of the sources and sinks that we provide out of the box, we rely on the entire Spring ecosystem. So Spring Data, all of the various Spring Data projects are involved. For instance, the Cassandra support, as well as everything to the simplest relational database support building on JDBC template. On the Spring Task side, we build on top, we support running batch jobs as well as simple tasks. So the Spring Batch is involved there. We use Spring Security within the Dataflow server itself. And pretty much if there's a Spring project, it plays a role somewhere.
Great, thanks, Mark. Next question, I appreciate that. So yeah, it seems like it's definitely building on some mature foundations. So thank you for that, and I think that's important for people to realize. Next question comes from Ricardo, who's curious if you could elaborate on the future plans for Spinnaker a little bit.
Yeah, Mark and I are here in the same room, and we both smiled when that question came up because we're actually meeting to discuss that very topic today. What we want to do, the one thing we haven't done yet, as I mentioned in the webinar, is handling changing the stream at runtime. Like one scenario would be going from version 1 of your app to version 2, or maybe changing some properties of it. And we're deciding what the right balance is of how much we want to write ourselves in terms of tearing down, let's say, building up, a couple instances of version 2, let's say, of your transformer, and then tearing down instances of version 1. So we would like to delegate to Spinnaker, in particular when we get to very complex scenarios where, for example, you might have a scheduled time that you want to go from version 1 to version 2. And the pipelines they have in Spinnaker, allow you to, explicitly incorporate, steps that can do so-called canary analysis. So you deploy a version 2, and it has a workflow where it can check basically an endpoint to see if it's healthy, and then slowly roll in the upgrades. So all that functionality is pretty sophisticated, has a very nice UI, and we'd like to leverage that. sort of the open question at the moment is, do we want to provide a very simple strategy that we implement ourselves? Not quite sure, but Spinnaker would be great because it automatically supports, a lot of the target environments we have. It supports Cloud Foundry. I should mention as well, if you go to GitHub and look at, or I believe we made an M1 release of Spring Cloud Spinnaker. So basically, you build that project, you get a jar file, you push that jar file, to Cloud Foundry, and you get a little UI. And basically, it's kind of like a poor man's tile in a way. That app actually deploys Spinnaker onto Cloud Foundry. So if you want to try Spinnaker with Cloud Foundry, it's ready today. You can kick the tires. We'd love to get feedback. So that's our plans. That's an important thing for us. We're aiming for in the 1.2 time frame of Spring Cloud Dataflow.
That's really exciting. Awesome. Thank you so much. Yeah, a lot of interest in Spinnaker and other CD tools these days, for sure. I'd be, as a side note, I'd be interested at some point to hear a little bit more about the concourse plans as well. Ricardo had a couple more follow-up questions, if that's all right. He was curious if you could elaborate on how the Dataflow server itself scales. Yeah, I imagine that kind of changes depending on platform, but maybe we could use the Cloud Foundry instance as an example, as a for instance.
Yeah. Sure.
You can specify.
Architecturally, it's a fairly simple way in which it scales. Our state is stored in a database, and there's no state in the server. So basically, you scale it as you would almost like any other web app. You can just scale out the number of instances, put it behind a load balancer. In certain architectures, maybe you can even put them in different regions. So you set it up basically and scale it as you would scale any other sort of web app that talks to a database. The only other thing it needs is credentials and connectivity to the platform where we launch things. So if it's Cloud Foundry, it needs connectivity to those credentials, to the space. Similarly for Kubernetes. We do, at the moment, only support deploying into one space in Cloud Foundry, or one account, basically, whatever an account maps onto. We don't yet support different accounts. And that's actually another interesting aspect of Spinnaker, is Spinnaker is already sort of aware of multiple spaces, multiple accounts, and can move things between them.
Okay, Mark, I think last question before we have to sign off. Again from Ricardo, and he was just, if you could keep this one kind of short, because I think we got to wrap it up. Just talk about alignment between Spring Framework 5 and Spring Cloud Dataflow. I mean, you already touched on the reactor integration a few minutes ago, but.
Yeah, I think that's the big one in terms of us relying on the same dependencies and leveraging that. I mean, the other thing is that the features that are in Spring Framework 5, right? They are going to obviously Spring Boot will be picking up Spring Framework 5 at some point, and so we can start to create sources and sinks that utilize some of the new features. For example, the functional web framework that's released. So that's kind of important, if you're choosing to create your own custom applications. You might want to create a custom HTTP source of some kind, and that would work very well picking up the new features in Spring Framework 5.
Great. Thank you so much. And folks, if you're looking to get a hold of bits, just go to the project page, and you'll see the instructions for cloning the repository. So it's not sort of your usual Maven coordinate lists. Easiest way to get a hold of the bits is to clone the Dataflow repository, and that link is available for you on the resource tab, and again on the slide right here if you just go to the top link. We hope to see you on a future webinar. Thank you so much. Mark, anything you want to say before we sign off and call it a wrap?
We really do need feedback, right? It's very important for us. So, any channel that you find preferable, Stack Overflow or GitHub, if there's a bug, those are the two main channels that we monitor quite closely.
All right. Thanks so much, guys. Have a great day, everyone, and keep an eye out on the Spring blog for announcements about future webinars. Hope to see you again soon.
Bye-bye.